Hello and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Space Telescope Science Institute. Tonight's talk, Shaping Galaxies with Supermassive Black Hole Winds by Mr. Revalski. I want to thank our amazing tech team, Thomas Marufu and Grant Justice. They have been helping us transform from our live audience in the auditorium to our online only. And I will say that our lecture series will continue to be online only until further notice. Next month, we have a special date. It will be on January 19th. We're skipping the first Tuesday because it's around New Year's. We're skipping the second Tuesday because it's the American Astronomical Society meeting. And we're going to the third Tuesday, January 19th, in which we have an amazing talk for you, The Darkest Secrets of the Universe, from Rajaguhatha from University of Santa Cruz. This is one, you're really gonna enjoy this, I know. In February and in March, we will both be meeting on the 2nd of the month. And because we were quite sure how long all this coronavirus stuff would last, we hadn't scheduled yet, but it's now time to start scheduling all throughout 2021. So don't worry, as always, I will make sure we have speakers in February and March. Where can you find out that information when it pops up? Well, of course, you can go to our website. If you just go to stsci.edu/public-lectures, you will find this webpage talking about it. You can see in the lower left, there is the links to our webcasts, both our YouTube playlist, as well as our webcast archive on the Space Telescope site. And in the lower right, you can see how you can subscribe to our announcements and get an email once or twice a month about the public lectures. Also on the website are the links to the individual lectures. And if you click on one of those lectures, you get the full detail about it. After it's been recorded, you can view the webcast on the STSCI webcast site or down bottom on the YouTube site and get all the information about the speaker and the abstract. For email, well, the announcements, you can just sign up at the website as I showed you previously. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. If you do subscribe to our YouTube channel, you'll get new notices of new videos as well as reminders of these live events. Finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. On social media, we do social media for the Hubble Space Telescope, for the upcoming James Webb Space Telescope, and for the Space Telescope Science Institute. And those institutions are represented on Facebook, Twitter, YouTube, and Instagram. So a whole lot of social media presentation for you. Myself, I do a tiny bit on Facebook and Twitter. If you want to follow me, please do so. And now, the news from the universe for December 2020. Our first story tonight, the fading glory of supernova 2018 GV. This is the galaxy NGC 2525. And as you can see, it's a nice spiral galaxy. This is a ground-based observation from the Carnegie Observatory. And you can see that's got some interesting spiral structure and everything. But ground-based doesn't quite capture the real detail in there. That's the Hubble image. Yeah, isn't that amazing that you get the resolution by getting up above Earth's atmosphere? You get an amazing resolution. Let me go back. Here is ground-based, and here is Hubble. Yeah, kind of great. But there's also one thing kind of interesting. I don't know if you guys saw it. Watch carefully. All right, we'll go back to the ground-based. Now see if you can see something pop on when we go to the Hubble. Did you catch it? It's right up here. That is not a star. That is an exploded star, supernova 2018 GV. Now it looks like a star, but really it's a supernova explosion, which is extremely bright. All the other stars you see in this image, they're not in the galaxy NGC 2525. They're in our own Milky Way galaxy. Remember, as we look out through our Milky Way galaxy at distant galaxies beyond, we go through this screen of stars. So the stars you're seeing in this image are actually very close to us. They're inside the Milky Way. Whereas 2018 GV is actually located in NGC 2525, millions of light years away. It has to be incredibly bright so that we can see it that far across the universe. And that's one of the important things about supernovae, is that we can see them occur in other galaxies. And so this one was first observed with a ground-based telescope in January of 2018, and Hubble started following it in February of 2018. And Hubble was able to watch as it faded away. So this is a close-up of supernova 2018, starting in about February 2018, going for about 1 year. And it's a movie, so we're going to play it through, and you can watch the star fade away and go back and looking. It's like a small one. This is only over the course of a year. Supernova actually fade over the course of about 3 or 4 years, at least for astronomers to follow them. And you can watch, and you can see we plotted a graph to show you the brightness at peak, and then following and fading down over time. That's actually kind of important, because the way a supernova decreases in its light curve from its peak magnitude down as it fades away actually tells us a lot about the physics of the supernova. There are different types: type 1a, type 1b, type 2b, type 2n. I hadn't heard of that until I looked at this chart earlier today. That's the hypernova stuff. And you can see how there are various ways of it falling. That tells you, and there are certain supernovae that are really important for cosmology. These are the type 1a supernovae. And here are two others that occurred in other galaxies: supernova 1994D and supernova 2011 FE. And by looking at these supernovae and finding out how they decrease and understanding that gives us their maximum brightness, which gives us distances to these galaxies, which when we measure the redshifts of these galaxies helps us refine the expansion rate of the universe. Right? This is actually part of a large project called SHOES, which is some convoluted acronym about supernova with Hubble to measure the expansion rate of the universe. Right? And so it's a very large project looking for these different distant supernovae in these distant galaxies to measure the distances and the redshifts and measure the expansion rate of the universe. So this is just one more piece in that puzzle, but it's very nice that Hubble was able to observe it many times over the course of a year to truly watch and see the fading glory of that supernova. Our second story: Arecibo, over and out. This is a sad story to tell, because it's about the Arecibo Radio Observatory, which is located, as you might guess, in Arecibo, Puerto Rico. Arecibo is located in the mountains of Puerto Rico in a natural sinkhole. And using the natural sinkhole, which already does most of the shaping for it, they were able to create a radio dish 1,000 feet across. It was built in the 1960s. It started operation in November 1963. So it has been the largest single dish radio observatory until 2016. For over 50 years, it was the largest single aperture radio telescope. It's been used for radio astronomy. It's been used for radar astronomy. They can actually send out signals with it. It's been used for atmospheric science. And it's also been used for the search for extraterrestrial intelligence. They actually sent out a signal out that maybe somebody somewhere will actually see. Or you might remember it was seen in the search for extraterrestrial intelligence in the movie Contact, starring Jodie Foster. That movie came out in 1997. Of course, That's sort of a geeky movie. It was based on a book by Carl Sagan. I'm sure most people remember the Arecibo Radio Observatory for its appearance in the James Bond film GoldenEye, where Pierce Brosnan and Sean Bean had this big fight out on the radio array in the center of the dish. Okay. Yeah, that never actually happened. But, you know, people, uh, uh, they actually filmed it while Arecibo was undergoing undergoing repairs, but the scene that they filmed was actually filmed with green screen around it, so they didn't actually get out there in front of it. They did various scenes. All right, so unfortunately, not even James Bond can save the Arecibo Observatory from the ravages of time. And this year has been particularly bad. In August of this year, one of the auxiliary cables, you see this structure that's holding up the main radio platform, receiver platform, one of the auxiliary cables snapped in August. They think that it was some sort of a manufacturing flaw in one of the bolts holding it together and anything. And then, you know, they did the analysis and they said, okay, the remaining cables should be able to hold it. But on November 6th of this year, one of the main cables, not an auxiliary cable, one of the main cables snapped. And there was a significant damage, which you can see in this big picture, but let me bring up a close-up. And you can see the kind of damage that was done. And in mid-November, around November 19th, I think it was, the National Science Foundation, which runs this observatory, announced that it would be decommissioned, that they would not be able to repair it. It would cost too much. They didn't have the budget for it. And that the world's, one of these iconic telescopes would be mothballed. However, things still kept happening. Over the weekend, several wires within cables snapped, and around 8 a.m. this morning, there was catastrophic failure. The whole main array fell into the dish. 900 tons of receiver platform fell over 400 feet down and smashed into the radio dish. The news of this spread like wildfire across the astronomical community this morning. And I finally found this image from the Science magazine. And it's just, yeah, it's 57 years of this telescope. It's endured hurricanes and earthquakes, and unfortunately, that is it. So I will always remember the Arecibo Observatory like this in its heyday while it was producing amazing science across many fields. Started in 1963, decommissioned in 2020. The Arecibo Observatory has had its last radio transmission. Over and out. And now to our featured speaker. Our featured speaker is Mitchell Revalski, and he has been with the Space Telescope Science Institute for about a year, a little longer than a year. He is a postdoc, which is what you do after you've finished your graduate work, you get your PhD, and then you do some postdocing before you then get your faculty job. So this is actually probably the most productive time of your career where you're able to sit there and really do your research right. He got his PhD at Georgia State and his undergraduate work at the College of New Jersey. And he and I were chatting earlier today. He does rock climbing, and he also does swing dancing, which puts he and I have something really interesting in common, because I did ballroom dancing at the University of California, Berkeley. And both of us met our wives at the dance club. All right. So you never know where you're going to run into an astrophysicist, but it turns out that maybe a dance club is a place to find one. Can't guarantee your mileage may vary on things like that. Ladies and gentlemen, Dr. Mitchell Revalski.
All right, thank you so much, Frank, for that kind introduction, and also to everyone for joining us online this evening. Hopefully after the sad news of Arecibo, I can uplift your mood a little bit by giving you a tour of supermassive black hole winds and show how they basically shape nearly every scale of the observable universe. So in the background here, we have this stunning multi-wavelength image that shows different facets of these black hole winds. And it's my hope that by the end of the talk, you'll have a strong conceptual picture of how supermassive black holes interact with the galaxies that they live in. So I'll start with a little bit of background on supermassive black holes and galaxies and how we study them, and then go ahead and examine the role of supermassive black holes in shaping their galaxies, starting from the very smallest scales, moving out to the very largest scales. So starting at the beginning, when we look out into the universe, we see galaxies almost everywhere. And so this image that you're seeing is the Hubble Ultra Deep Field, which is one of the deepest views of the universe ever captured by humanity. It required the Hubble Space Telescope to cumulatively look at the same patch of the sky for nearly 11 days, which is about 400 orbits around the Earth. And so in this image, we see galaxies that are relatively close to us, and we see galaxies at the very furthest extents of the universe. And so in astronomy, we're in this very unique position because we can actually look back in time and see these galaxies as they're growing. The further away we look, it takes the light longer and longer to reach us. And so we're seeing these galaxies as they were a very long time ago. Now, despite all these different types of galaxies you see in this image, they're all made of the same fundamental building blocks, and that's stars, gas, dust, and more exotic components like black holes and dark matter. So we have all these components. We can still classify galaxies into different types depending on how much they have of these components on their appearance, such as spiral galaxies, elliptical galaxies, irregulars. We'll talk about that a little bit more in a minute. But despite the apparent kind of emptiness in between these galaxies, there really is gas everywhere. We have gas within galaxies, we have gas around galaxies, and we have gas in the spaces between galaxies. And so depending on the temperature and the density of that gas, we might need to use different types of telescopes to see it. But I want you to keep in mind this picture where galaxies are just filled and surrounded with different types of gas. And in order to study the connection between galaxies and their gas and their supermassive black holes, we're going to use two of the most fundamental tools of astronomy, which are imaging and spectroscopy. So those of you who frequent these public lectures have probably seen many representations of the electromagnetic spectrum. And I really like this image because we're looking at the same galaxy, M51, the famous Whirlpool galaxy, at each different section of the electromagnetic spectrum. So light comes out in the form of photons. We can specify its energy by a wavelength. So starting up here at the top left, we're looking at the longest wavelengths, the radio, moving to the right to the shortest, most energetic wavelengths at gamma rays. So as we sweep through the electromagnetic spectrum with different telescopes, we're probing different portions of the galaxy and its gas. So starting here on the left in the radio, we're probing the very cold, cool, dense gas that is basically the reservoir from which stars can form. And as we'll see, the radio will actually also be useful for probing some of that most energetic phenomenon within galaxies. As we move over to the right, we're looking at the infrared, and here we're starting to probe the warm dust and the cool stars within galaxies. And this has been most famously done using the Spitzer Space Telescope. As we continue on into the center, we're looking at optical or visible wavelengths. And these are the colors that our eyes are sensitive to, that we're able to detect and perceive. And this is probing gas that's maybe a few thousand degrees, looking at some of the hotter stars. And by far, one of the most famous and successful observatories for doing this type of astronomy is the Hubble Space Telescope. As we continue on, moving to higher energies, looking at the ultraviolet and X-rays, we're looking at gas that's tens of thousands or even hundreds of thousands or millions of degrees. And so this is often done in the ultraviolet and the X-rays using instruments such as the Chandra X-ray Observatory. So this is the first tool in our kit in order to understand the universe. We have an image, we open our telescope up, we allow the light to hit a detector, and it shows us the distribution of gas and dust and stars within galaxies. The second tool, of course, is spectroscopy. And so a famous saying is that if a picture is worth 1,000 words, then a spectrum is worth 1,000 pictures, meaning that we can get an enormous amount of information from the spectrum of an object. We can learn a lot more than we could by simply having an image. So spectroscopy is the process of taking light from a galaxy or a portion of a galaxy. We pass it through a spectrograph on board of our telescope. In this case, I have a little Hubble Space Telescope. And then we spread it out as a function of wavelength or color. So either by passing it through a prism or bouncing it off a grating, we spread that light out and then we record the intensity of the light as a function of wavelength. So we do this, we can take this spectrum on the right and we can measure the intensity at each color and we get a more familiar spectrum. And this has a couple key features that are really going to help us in our studies. First, we just have the underlying level of light at all colors. This is the continuum emission. This is primarily coming from hot stars and dust within a galaxy. And then on top of that, we can have these very straight, narrow features called emission lines. So we have this excess of light at a very specific color. And this is coming from the gas. This is coming from individual atoms, which have electrons going around them. And if those electrons are excited and de-excited, they jump between very discrete, very well-known energy levels. And so you get a very specific color, a very specific wavelength of that photon. The converse of this is absorption lines, where we're basically absorbing a very specific color. And all these features are very important because they tell us a lot of information about the gas. Most specifically, they tell us about the velocity of this material. So the locations of these emission lines are very well known from measuring them in the lab, but due to the Doppler effect, if objects are moving either toward or away from us, the lines will be blue shifted or red shifted, moving to shorter or longer wavelengths within the spectrum. So basically, we can use the positions of these lines to measure the velocities of things in space. So we're going to go ahead and apply these tools to the different portions of galaxies. And so here we have on the left an example of more of an edge-on spiral galaxy, and on the right we have more of a face-on spiral galaxy. And down in the very center we have the nucleus. This is the very center of the galaxy. And around that, we have the bulge. And this is basically kind of a semi-spherical distribution of stars that are all orbiting around the nucleus, typically made up of older stars as compared to hotter, younger stars. In this case, we also have spiral arms. And these are regions that are slightly more dense in hot stars and gas and dust. And they make these very intricate shapes that we can see in these spiral galaxies. Now, of course, these are not the only type. There's also ellipticals, which you can almost think of as just one giant bulge with much less gas and much less dust, as well as irregulars and types like that. But a profound discovery to come out of the last few decades is that almost all massive galaxies at their centers have a supermassive black hole, abbreviated SMBH. Now, in this case, I've drawn these dots, and they're actually much too large for the scale of the galaxy. Supermassive black holes are actually very small at the distances of these galaxies. And so a logical question might be, well, how do we actually know that they're even there? And so the best evidence of this comes from looking at the center of our very own galaxy. So here we're looking at the center of our galaxy, and we're tracing the motions of stars around the center over the course of about 20 years. And by doing this, we can see that all of these stars are orbiting around this central point marked by a star. However, when we point the majority of our telescopes there, we don't really see anything. So based on the physics that we know, we can see how fast these stars are moving, how tight their orbits are, and we can calculate how much mass has to be there to actually hold those stars in those tight orbits. And it turns out to be millions of times the mass of our own sun. So we have something that is very, very massive, not really emitting any light, and it's very, very dense because these stars are orbiting very close. And so the only objects that we know of that can be that dense and that massive are supermassive black holes. These are objects that range from millions to even billions of times the mass of our own sun, and it's all crushed down into a volume about the size of the solar system, depending on its mass. So this is an incredible result that was finally really fully solidified and recognized just this year with the 2020 Nobel Prize in Physics, which was recently awarded to these three individuals for their pioneering work to prove beyond a reasonable doubt that supermassive black holes exist and are at the centers of the majority of galaxies. So for the most part, when we look at galaxies, we have this kind of invisible or indirect view of supermassive black holes. But that changes when we look at supermassive black holes that are actively growing or eating material, and these are active galaxies or active galactic nuclei. So here on the right, we have an artist's conception of basically a supermassive black hole. Material in the galaxy works its way down into the center, and as it starts to fall into the strong gravitational potential of the black hole, it will become compressed. It'll form an accretion disk of material that's accreting onto the supermassive black hole. It will heat up, and it'll emit an immense amount of radiation all across the electromagnetic spectrum, from the radio to the infrared, the visible, the ultraviolet, the X-rays, and onward. So the way that we kind of characterize this process, that we talk about different active galaxies, that we compare their power, is through what's called the luminosity. And so this is the total amount of energy that's being emitted at one time due to this process of material falling onto the black hole. And this ranges from about 1,000,000 times the luminosity of our own sun, which is about the same as one really bright, massive O star, the largest stars we see in most galaxies, all the way up to hundreds of trillions of times the luminosity of our own sun. So in the most powerful active galaxies, the amount of radiation coming from very near the supermassive black hole can actually outshine the light of all the stars in the entire galaxy. So this is going to be a very fundamental parameter that we're going to use when we're talking about these active galaxies: the luminosity, the total amount of energy that's being radiated by this process of material falling onto the black hole. Now, all this energy has to go somewhere. It doesn't just disappear. And so this is where our supermassive black hole winds come into play. This energy in the form of light, in the form of photons, is traveling out back into the galaxy. It can interact with the gas, it can excite it, it can ionize it, cause it to glow like a neon sign. And more than that, we have such intense radiation that it's actually exerting a force. It's actually imparting momentum onto this gas and pushing it potentially away from the supermassive black hole. And so this is what we call mass outflows or winds. I'm going to use those two phrases somewhat interchangeably. Now, these appear in kind of two main forms. The first is these mass outflows, where we have radiation that's traveling out into the galaxy. It's finding gas somewhere, exciting it, and then moving it away from the supermassive black hole. And then we also have radio jets. And so this is a somewhat different phenomenon. And so here what we have is very close to the supermassive black hole. There's an immense amount of energy. We have twisting magnetic fields, all sorts of intense physics. And this is basically able to launch a pencil beam of particles away from the supermassive black hole at very, very high velocities. And so these are much narrower, they're much more directed, but they may have much less material. And so these are kind of the two main types of outflows that I'm going to be focusing on tonight. So with this, we have nearly everything that we need to investigate these supermassive black hole winds. Let's go ahead and just paint the big picture. So here on the right, we have an artist's kind of version of a typical, say, Milky Way-like galaxy. And we like to measure distances in astronomy using parsecs, where a parsec is about 3 light years. So anytime you hear a parsec, you can think 3 light years. And just like grams and kilograms, we use suffixes to give larger distances. So 1,000 parsecs is a kiloparsec. So everything I've shown you so far, the supermassive black hole, its accretion disk, this whole energetic environment, is all contained down at the very center of the galaxy. If you look at this image on the right, I'll highlight the centermost portion. So all of this is contained on scales of less than a parsec, nearly less than a light year. So I've highlighted that with a single red pixel on this image, and that's actually too large. It should be even smaller than that. And so that's just to highlight just how tiny these very massive, dense objects are on the scales of their galaxies. The next scale as we move out is the galaxy bulge. And so this is on scales of about 1,000 to 3,000 parsecs, or 1 to 3 kiloparsecs. Continuing on past that, we have the stellar disk of the galaxy. And so this is basically the extent of the galaxy as traced by the stars. And this varies depending on the type of galaxy, but it might be something on the order of, say, 30 kiloparsecs, which is about 100,000 light years. And finally, in the region outside of the galaxy, where we might not see many stars, but we still have lots of gas, this is the circumgalactic medium, or the circumgalactic region around these galaxies. So these are kind of the 4 fundamental scales that we're going to focus on when looking at these supermassive black hole winds. So now you have all the background you need. We can dive in, and we can tackle this from 2 points of view. We can look at these winds from simulations, or we can look at them from observations. So simulations and observations both tell us something somewhat different, but they're complementary. By learning from one, we can use that information to inform the other and then rotate through to try to understand the physics at work. So we're going to go ahead and start with simulations. So let's take the universe, let's put it in a box, let's apply all the physics that we know, and let's see how it evolves over time. So in this simulation, we're looking at the temperature of gas in the universe from the very earliest times moving towards the present day. And so what you see here is this long filamentary-like structure, all these different pieces of gas, and we have the very cool gas in blue, warmer gas in green, and the hottest gas in red. So these big structures here, these are whole groups of galaxies, clusters of galaxies. We're looking at the very biggest scales. And what you start to see are these pockets of red basically exploding out of these groups of galaxies. And so these are our AGN. These are our supermassive black holes that are eating material and pushing an immense amount of energy and radiation out beyond the galaxy and heating up and moving this gas. So these simulations are absolutely incredible. This one in particular is from the Illustrious group. And so these allow us to control the different aspects of what's going on and understand the physics in detail. Despite how incredible these simulations are, we still just don't have the computational power to simulate all the different scales that we just talked about. So if you want to simulate material falling into a black hole, simulate individual galaxies, and then simulate the entire universe, we just don't have the computational power to do that. And so what we do here is we use different numerical recipes. Basically, we say, okay, on the smallest scales, let's just say that we know how much energy is being injected by these AGN, and then we'll follow it and watch what happens. And so one of the things that's very critical here is the result that you get depends very strongly on how you tweak those parameters. So here towards the end of the simulation, you can see that we have all this hot gas that's permeating all throughout between these different galaxies and clusters of galaxies. But now if we go ahead and update the physics a little bit, and we look at what happens if we try to understand the efficiency of how this radiation is produced and how it moves out and couples with gas. If we go ahead and fine tune those parameters based on what we know now, we see that in just a few years, these simulations give somewhat different answers. So we still have this hot, excited gas, but now on the right, we can see that it's very hot, but more condensed. It's held more closely to these clusters, these groups of galaxies. And so the overall picture is somewhat different. And so the way that we can improve these simulations and inform them is by going ahead and actually doing detailed observations of these supermassive black hole winds to understand just how powerful they are, to understand just how they work, and then we can iterate between simulations and observations to learn all the physics involved. So now we're ready to transition to observations, starting here with our big picture. We're going to go ahead at the closest in scales right near the supermassive black hole in the accretion disk on scales of less than a light year. And so because we're so close to the supermassive black hole, we're generally looking at the highest energy radiation, which is most often observed in the X-rays. So early missions looking in the X-rays showed some sort of signature in the spectra. There was something going on, but X-ray spectroscopy is really difficult. X-rays are very high energy. If you try to bounce them off a normal type of mirror that you're used to looking at, they'll just go right through it. And so you have to build a very specialized telescope with a series of ring-like mirrors that will basically bounce that photon and get it down onto the detector where you want to analyze it. And so this was really revolutionized by newer space missions such as the Chandra X-ray Observatory, Suzaku, and the X-ray multi-mirror mission telescope shown here on the right. And so after looking at more and more of these active galaxies and looking at a large archive of data, really just in the last 10 years is when we've been able to establish that there is indeed these winds very close to the supermassive black hole. And as the title alludes to, these are called ultra fast outflows, or UFOs. Yes, that is actually the acronym. So you can see here on the right is one of these X-ray spectra. So we're looking on the horizontal axis at the energy of the light, and on the vertical axis, the brightness of that light. And we can see here that we have this emission line feature, which is coming from very close to the supermassive black hole. Turns out to be from iron K alpha, very highly ionized iron. And then we see here this absorption feature. And so with some very detailed and careful modeling, we can figure out that this absorption line is coming from the same excited state as this emission line. And this corresponds to a very, very large shift, a very large Doppler shift. So as we talked about, we can use those shifts to determine the velocity. And in this case, it works out to be 15% of the speed of light, which is absolutely insane. So by looking at more of these objects, we found that ultra-fast outflows can move at up to 30% the speed of light. That's something like 60,000 miles per second. That is one serious speeding ticket. So what we're seeing is we have this artist conception on the right with the supermassive black hole in the accretion disk, and this material is being launched from very close to the accretion disk, and then it's absorbing some of the light as it's moving, and that's what we see as that absorption feature in the spectrum. Another interesting feature of UFOs is that when we look at them and we revisit the same galaxies, we see that they change on time scales of months to years or even faster. And so this is telling us that these are not nice, steady, constant types of phenomenon, but they're very chaotic and tumultuous. They're constantly changing. And this could be really important because we have gas that's moving very, very fast. And so it may actually be able to sweep material out and regulate how fast the black hole is growing. As the black hole is eating, it's actually generating the energy that is pushing away its fuel. It's pushing away its supply of gas that it would otherwise try to accrete. And so the question is, well, is there any evidence that this is what's really happening? And indeed there is. So looking here, on the vertical axis, we have the mass of these supermassive black holes in terms of mass of the sun, moving from 1 million to 10 billion. And then we have the mass of the bulge, that large semi-spherical distribution of stars around the center of the galaxy, and the velocity of those stars. And what we can see is that these two things are correlated, meaning if we have a measurement of one, then we have a reasonable estimate of the other. And now you might say, well, that makes sense, right? Larger galaxy, larger bulge, larger supermassive black hole, but there's no necessity for it to be that way. And what I mean is that even though supermassive black holes are so dense and have such a strong gravitational pull, it's only when you get really close to them that their gravity starts to dominate. So within a galaxy, the supermassive black hole is only dominating the gravity in a region maybe a few light years or smaller around it. Whereas the bulge of these galaxies is on scales of thousands of light years. And so they're just not gravitationally aware of each other. It's kind of like holding a magnet at a paperclip a mile away. The effect is just too weak to really matter. And so this is one piece of evidence that maybe these two individual entities basically evolved together. Maybe the black hole and the bulge grew up together, exchanging energy and information through these winds and through this exchange of material that's being pushed out to larger radii. That's not the only interpretation of this result. There are other ways that you might be able to generate this, but this is one piece of evidence in support of that picture. So the second stop on our tour of supermassive black hole winds is now looking within the galaxy bulge. So now we're looking on scales of a few thousand light years. And so early studies in this regime kind of showed that there were non-rotational motions. So it was clear that gas was doing something that wasn't just nice and simple galaxy rotation, but it was really revolutionized with data from the Hubble Space Telescope. Because as Frank mentioned, we get above the atmosphere, we can see extremely small details. And the critical piece here is that this is the first scale as we move away from the black hole that we can actually spatially resolve. Meaning when we look at stars, they're infinitesimal small points of light. When you look at the moon and planets, they have a defined physical size on the sky. And so we can actually resolve the bulges of galaxies. So we're going to go ahead and start at a galaxy and zoom in on its bulge. Here's an example of NGC 4151. It's one of the most nearby and well-studied active galaxies because it is so nearby and very bright. Here we can see it has these extended spiral arm structures. It has this ring of hot young stars that are forming that are surrounding this yellowish older bulge of stars. Now, this is an incredible ground-based image, but as Frank mentioned again, we're just still limited by the Earth's atmosphere sometimes. So if we go ahead and zoom in with the power of the Hubble Space Telescope, we get a much clearer picture. Now we can see individual clumps of stars that are forming within the galaxy. We can see these dark spiral dust lanes working their way into the center around the bulge, and we can start to see some hint of this bright active nucleus. Now, like any good criminal investigation show, all you have to do is hit your magic enhance button again. Okay, of course, it's not quite that simple, but if we zoom in once again, we get this incredible image of this bulge scale outflow produced by Judy Schmidt. And so down in the very center here, we have this supermassive black hole and accretion disk, our source of energy, and that radiation is traveling out into the galaxy. It's exciting this gas, it's making it glow like a neon sign. And so we can see very clearly here that there's an impact on the galaxy, but what is this gas really doing? How do we know where it's going? How do we know what its fate is? And so, of course, the second piece to that is by using spectroscopy. So if we isolate a portion of it using the Hubble Space Telescope, looking at just a specific portion of the galaxy, as we showed in some of our earlier example spectra, well, if the gas was just sitting there, let's say we were looking at 2 emission lines, we might just expect nice straight lines. Galaxies generally rotating, and so one side is moving towards us, another side is moving away from us, and so we'd expect some sort of red shift and blue shift on either side of the galaxy. When we look at the actual data for this target, we see indeed some of the gas is rotating, but there's also this gas moving at much higher velocities, at higher blue shifts and red shifts. So while the galaxy might be rotating at a few hundred kilometers a second, this gas is moving at maybe 1,000 kilometers per second. So this is that clear signature that on one side of the galaxy, gas is moving towards you, and on the other side, gas is moving away from you. Now, this is an incredible result, but it's kind of tough to picture the geometry here, what's really going on. So let's look at a model of this, starting down right near the supermassive black hole where all this radiation's coming out, and then let's zoom out onto scales of the galaxy. So we can see here we have this blue disk of the galaxy rotating around, and this radiation is traveling out into the galaxy. It's exciting it, it's ionizing it, and then it's pushing it away from the supermassive black hole. So this is an area of research that I've been very interested in, and we've learned a number of things for these types of supermassive black hole winds. So the first is that the gas can probably be launched at a bunch of different distances, meaning it's not all coming from right near the supermassive black hole, but as this radiation travels out, it sees the gas there, it excites it, and then it starts pushing it. Now, while these are not moving nearly as fast as the ultra-fast outflows, they're moving at less than 1% of the speed of light as compared to nearly 30% of the speed of light. Because they're spatially resolved, we can work out how much material is there in detail. And it turns out that these outflows can carry several million or even tens of millions of solar masses worth of gas. It's a lot of material. And so the impact here is that this may reduce star formation in the inner regions of the galaxy because we're evacuating the gas, which would otherwise be available to form stars. In addition, we're also heating that gas up. Gas needs to start to cool down to collapse under gravity in order to form stars. Now, this is kind of a general picture, and it's not the case for every single galaxy. In some cases, gas is actually driven out, impacts other gas, and then may trigger star formation. So it's not a one-size-fits-all in terms of what we see the impact of these outflows being, but this is kind of a general picture that's emerging. So with that, we're ready to move to the third out of 4 spatial scales of our tour of supermassive black hole winds, and that is scales of the galaxy stellar disk. So these are basically on scales of the entire galaxy. Now, you might remember from earlier that I mentioned that the luminosity of these active galaxies is a key factor. And so if we're looking for outflows on the scales of galaxies, we generally need more luminous active galaxies because we need more energy to push gas at these large distances and to push large amounts of gas. And so this is more commonly observed further back in the more distant universe. And so studies of this type have been done with a number of telescopes and instruments. And one of the key instruments that's really revolutionized this is the Atacama Large Millimeter and Submillimeter Array, or ALMA. And so that's shown on the right here. This is basically a series of radio and millimeter dishes that are all pointed at the same object. And we're basically taking the information from each of them, and through a process of interferometry or interference, we're bringing that data together in order to get an image that is as good as if we had one ginormous dish, as we saw earlier. And so in this case, you can separate these telescopes by up to 16 kilometers. And so we're getting an image as if we had one massive telescope. So let's go ahead and look at one of these. So this is an example of a galaxy. Now it's much more distant, and so we don't get that fine, exquisite detail in the image necessarily, but this is actually quite a large galaxy. We're looking at excited gas here on the scales of around 10 kiloparsecs, or over 30,000 light years. And so what we see looking at these galaxies that are further away, in this case, it's looking back nearly 10 billion years to a redshift of 2, is that it's not very simple to figure out what's going on. It's not just the supermassive black hole that's necessarily driving these winds. And what we found out is that stars actually make a very large contribution, sometimes the dominant contribution in these galaxies. And so what that's happening is basically stars are either forming very rapidly and their immense radiation is contributing to driving these winds, or as stars die through powerful supernova events that Frank showed earlier, they emit an immense amount of radiation that can also go ahead and excite and move this gas. So stellar outflows and stellar winds are worthy of an entire another talk in and of themselves. So this is just to point out that sometimes it's more than one mechanism at work. And this is a key place where we'll learn a lot more with the James Webb Space Telescope, because we'll be able to probe these galaxies on very small scales. We'll be able to look at them in great detail with high sensitivity in different portions of the spectrum than we can necessarily look at now. And so when we look at this galaxy in this image, we can go ahead and take a spectrum of it. And we have this first strong emission line, which is basically just from the rotation of the galaxy. And then we can see that we actually have a second emission line right next to it, which is coming from the same excited state. And this is gas that's moving at several hundred kilometers per second. And if we look at where this material is relative to the center of the galaxy, we see this big redshifted blob of material that's being blown out from the center of the galaxy, or from within the disk of the galaxy. So finally, we've arrived at the last stop on our tour of supermassive black hole winds, and this is the circumgalactic medium, or the scales around galaxies themselves. So here, as I mentioned, there are basically two forms of these outflows. There are these wide-angle mass outflows, and then there are these narrow radio jets. And so in this case, what we're often looking at on scales bigger than galaxies are these radio jets. So in this case, the particles within these jets can be moving very, very fast, typically maybe half the speed of light, but sometimes in excess of 99% the speed of light. These are some of the fastest phenomenon in the universe. So these are extremely fast moving jets. Now, again, these are often found in more luminous and more powerful and often more massive active galaxies. And so here on the right is an example of Centaurus A, which is a more nearby active galaxy. Here we can see it has some bright emission from stars. It has a dust lane across it. And if we zoom in and add in millimeter and radio data, we can see these powerful jets. So we can see these two jets here, which are pushing their way out beyond the galaxy to scales larger than the galaxy. Now, in this case, this is a more nearby example. Let's go to more powerful examples in the more distant universe. In particular, the impact of these jets is most clearly seen when we look at clusters and groups of galaxies where they have something to interact with. So we're going to start out with a Hubble Space Telescope image in the optical. And here we can see we have a large galaxy in the center. We have a bunch of smaller galaxies around it. But for the most part, it just looks like an image of galaxies. Now, when we go ahead and add in the radio information, in red, we can see this long extended radio jet starting near the center of the galaxy and then pushing its way out past well beyond some of the galaxies in this cluster. Now, even with these two pieces of information, we still can't fully see the impact until we add in information from the X-rays. And so we add that information in blue and put these all together, and we end up with an image that looks like this. And so what we're seeing here is this radio jet is moving out away from the galaxy, and it's actually carving out these kind of bubbles in this very hot, tenuous X-ray gas. So here is the overall view with these three different energy and wavelength regimes individually, and what we can learn from them combined. And so the kind of the overall picture that's emerging of these big, massive active galaxies with jets and clusters is that the jet is acting to basically prevent the gas from cooling and falling into galaxies to form stars. So naturally, the gas would want to cool, the gravity would pull it into galaxies, it should begin to form stars. And so this jet is basically keeping the gas out there, keeping it heating up. And in some cases, it can reduce the rate at which stars form by up to a factor of 10. So it's really quite powerful. And this is often denoted maintenance mode outflows or maintenance mode feedback, basically as the black hole is feeding and delivering feedback to its environment rather than actually pushing gas well outside the galaxies. We're basically just keeping it there and keeping it warm, and that way it can't collapse down to form stars. So with that, to kind of pull all of this together, I hope I've shown you that supermassive black holes and the AGN that they power have the potential to significantly impact their galaxies. So this may be on scales of the supermassive black hole and the bulge of the galaxy with these ultra fast outflows. It can be within the bulge and on the scales of the galaxy disk, looking at the rates at which stars form. And it can be on even larger scales, on entire groups and clusters of galaxies, where we're keeping lots of gas hot and moving around so that way it can't form stars and is impacting the overall formation of galaxy structure. So I'd like to end by coming back to where we started with this image of NGC 1275. And I hope now that this gives you a little more awe-inspire, as it does to me. What we have down in the center is this supermassive black hole that's eating material and putting an immense amount of radiation out into the galaxy and beyond. In this case, it's exciting that gas, it's pushing it away from the supermassive black hole out beyond the galaxy. And we can see even here that we're lighting up gas within the cluster in these long red filaments and strings, which contain millions and tens of millions or even more solar masses worth of gas. It's keeping it hot and it's impacting the entire environment around it. So if there's one real takeaway here, it's that the supermassive black hole resides at the very center on the very smallest scales of galaxies, and yet it has the potential to impact nearly every scale that we can observe. And with that, I would be happy to take any questions.
All right. Thank you, Mitchell. That was wonderful. It was great, especially the way that you worked and got across the idea that it does really go from, parsec scales and down to the supermassive black hole is a parsec scale object out to millions of parsecs when you get the giant radio jets. We had a lot of interesting discussion in the chat, but one of the things that people talked about was the correlation between the bulge mass and the supermassive black hole mass. And you sort of answered it a bit, but given the formation time scale of the two, that obviously means how quickly do they form, and do they form in the same time scale type thing?
That's a great question. So as I mentioned, when we look back at more distant galaxies, we're looking back in time, but these are kind of snapshots. So how does this evolve over time? So in the very distant universe, when galaxies are basically just starting to be built, that's when we have gas collapsing down. It's starting to form stars. It's starting to form disks. And that's when the bulge really begins to form. And so it's really from the very earliest portions of the universe where we can see that supermassive black holes and galaxies are beginning to form, that these energetic phenomenon are happening. So an important question is, well, how long does it really take to necessarily do this? That's not a question that I have a very sharp answer for, but what I can tell you is that it's timescales on the order of millions of years or more. And so we get that basically from looking at how long active galaxies are basically turned on for. So the majority of galaxies in the universe are basically quiescent. Their black holes are kind of hidden. They're not really eating. But by looking at lots and lots of galaxies, we can figure out that almost every galaxy should become an active galaxy for maybe 10% of its life or something on that order. And so we're talking about timescales of millions of years, sometimes maybe a bit more for sure.
Okay, great. Grant Justice has been monitoring the chat more than I've been able to. Grant, why don't you turn on your video and join us and bring us some of the best questions from our chat.
Sure, absolutely. So yes, the chat has been very active for this one. Black holes are always one of both online and our favorite subjects when we get it. So The first one that I picked out was, is the length of the ultra-fast outflows an indication of age or formation activation time for black holes?
That's a good question. So basically, these ultra-fast outflows are very, very close to the supermassive black hole. So we can't necessarily measure how far they extend, but we can figure out how long they've been there by looking at these galaxies again and again. And so in that context, often we see them sometimes appearing and disappearing on week or month timescales. But the real tricky part here, this is where things get almost kind of ghostly, is that sometimes they're appearing and disappearing just because we can't actually see them with our X-ray telescopes. And what I mean is each type of telescope is sensitive to a different wavelength range, a different energy range. And so if that outflow becomes so incredibly ionized and excited, it may still be there, but it disappears from our telescope and we basically just can't see it. Or on the other side of that, the outflow can get so dense and mass loaded with material that it's basically blocking the view altogether. And so in terms of what these ultra-fast outflows do, we know that they're close to the center of galaxies, but there's actually been some recent evidence that maybe they travel out further and then they push gas on the scales of galaxies on galactic scales. So there might be some interaction.
Okay, and that brings up another question that was sort of referenced, is that you talk about the speed of the ultra-fast ones, right, the UFOs. And then you talked about the speed of the stellar disk scale ones, but the ones that go all the way out, I mean, does speed correlate to the distance away? Is it, how much of it is just the density of the material it gets to plow through versus how much is the speed of the upflow?
Absolutely. That's a great question. So yeah, so for those kind of bulge scale outflows and galaxy scale outflows, we're generally looking at, a few hundred to a few thousand kilometers per second. And since we can spatially resolve them, we can actually kind of see how they change as they move throughout the galaxy. And so in a lot of cases, we'll see that it basically looks like the gas is moving faster and faster and faster. And then at some point it turns over and begins to slow down and slow down. And so there's kind of two interpretations. Either the gas is being accelerated and then decelerated because you're running out of energy to push it, or that gas is being driven from wherever it was in the galaxy. And the further away you get, you just have less radiation, so you can't push it as fast. So these definitely change in velocity as you move throughout a galaxy.
Okay. Grant, what's up next?
Yeah. So next up is, do supermassive black holes always begin as stars? Is there any other way that they can form?
That is an excellent question. If I had a full answer to that, I'd probably have a Nobel Prize. So the further back we look in the universe, we still see evidence of these supermassive black holes, and how they can possibly form so quickly, so early in the universe is definitely still a mystery. And so this is one of those things. There are certainly many great ideas out there. It's been worked on for some time, and this is definitely one of the key questions to push after with the James Webb Space Telescope.
So the answer is, we don't know, but we're going to find out.
That is correct, yes.
Quintessential science answer. What trait of black holes surprised or surprises you the most?
Oh, what an interesting question. What
Right?
trait of supermassive black holes surprises me the most? I think the trait that surprises me the most is how we picture these as having this immense gravitational field that just eats everything around it, which if you get close to the black hole is very true. However, if you're very far from the black hole, it's basically the same gravity as you might feel from a star or any other body. And so, for example, if you were to take the sun and pluck it out of the solar system and put a black hole with the same mass, which would be very small, a few kilometers in size, for the most part, all the planets would just keep going on in their orbits as they were. Things very close like Mercury might get perturbed a little bit, but in general, it's just a point source of gravity. And so that is one of the most surprising things to me, is that they're not just these monsters eating necessarily everything all around them, but once you get very close, things do get very intense.
Yeah, that's one of the hardest things to get across to the public, because mass media has created them as, oh, they're sucking in everything around it. No, black holes don't suck, guys. Okay, they're just gravitational entities. So we will be explaining that for the rest of our careers, unfortunately.
It's less of a headline if it's not trying to kill us all immediately or impending doom. So is it possible for emissions to restart Because one of the theories that you mentioned was black holes having a potential to freeze, as it were. Is it possible for emissions to come from a frozen black hole?
Absolutely. This is a fantastic question. So thank you for bringing this up. So in this picture, I've kind of painted the active galaxy is basically just continuously putting out energy. It's exciting this gas and driving it, but that all relies on material getting down into the black hole. And so that can happen from gas just working its way in, from minor mergers where little galaxies come in. And so it's possible for these active galaxies basically to turn on and off. So we can look at an active galaxy today and say, well, there's barely anything going on. But if we look at the larger scales, we'll see these echoes, these kind of light echoes or these remnants of much more excited gas at larger radii that tells us that at some point in the past, the active galaxy was much more powerful. And we've also seen the converse of that, where basically it looks like something is restarting, where we have this old radio jet that's basically dissipating, and then a new jet that is being launched much closer to the black hole.
All right. So on the online questions, that's more or less where I had. Frank,
Yeah, I'm checking to see if there are any
Yeah.
more.
Any came in during the
Yeah, there's one about chemical makeup of the gas. Is the chemical makeup of gas similar among galaxies, or is the proportion of elements significantly different from one galaxy to the next?
That's a very interesting question. So all the gas and dust and stars in these galaxies are made up of all the different elements we can see, primarily hydrogen and helium, but traces of everything else, such as carbon, nitrogen, and oxygen. And so depending on which distance you're looking at from the galaxy, those relative abundances of the elements do change. And so often we see near the centers of galaxies where stars have formed in the past and they process that material, we have higher metallicity, basically elements that are heavier than hydrogen and helium. Whereas at much larger distances, we might see much lower metallicity. So we have much less of those heavy elements. And this is another reason that I didn't have a chance to touch on as to why these winds and outflows are so important, because then we're taking some of that enriched material and we're moving it out onto much larger scales where it may not normally be. And so that's going to affect the way that stars form, gas cools, and all those sorts of details.
Okay. I actually have a pretty good one that just came in right
I was
now.
going to say, there's that's a good last question.
Yep. Do black holes die? And if so, how?
Do black holes die? So theoretically, there is a process known as Hawking radiation where black holes could very, very, very slowly evaporate. For supermassive black holes, the amount of time that would take is many times longer than the age of the universe. Even for small black holes made from smaller stars, it's still an exceedingly long time, and so we don't have any direct measurement of that. But otherwise, in theory, the black hole will just sit there forever until something comes by for it to chew up.
Well,
yeah.
Black holes, for at least for as far as we're concerned, black holes will be around forever. And I probably think, at least for my lifetime, we'll continually be learning about them. There's just the amount that radio astronomy and telescopes like Arecibo that we talked about earlier have contributed to our understanding of what goes on in the cores of these galaxies. It's just been amazing to watch over the decades.
Absolutely. We've learned so much, and yet we still have so much to learn. And so if we knew it all, then astronomy would not be fun. And so that's one of the most exciting things in astronomy.
If we knew it all, we'd be out of jobs.
It's interesting to see as well. Like Hubble's the same age as I am, so we have the same lifespan thus far. I can't wait for JWST to get into some of these.
I didn't want to mention it during the news summary, but Arecibo was started operation the year I was born. So it looks like I have a little bit longer longevity than Arecibo. All right. Well, thank you very much. Appreciate all of your help, Grant, in getting the comments out this. Everybody, next month, remember, it's January 19th, special date. We're skipping the first couple of Tuesdays for various reasons. It will be the Darkest Secrets of the Universe, Raja Guhathakurta from the UC Santa Cruz. We'll see you then. Thank you all for coming, and have a great day.